Now, let's take a look at the Loose Particles tab. During the manufacturing process of a loudspeaker, some loose particles of foreign material may stay trapped in the gap behind the diaphragm or dust cap. During operation at low frequencies, these particles randomly hit the diaphragm, making a click or pop noise. These defects are easier to catch at low frequencies, usually below resonance, where maximum driver displacement occurs. This algorithm can detect those loose particles as impulses in the sound emitted by a loudspeaker during a measurement. Loose particles is also useful for detecting digital artifacts like squelches or dropouts. Loose particles is available in all algorithms. So here on the tab called Loose Part, there is a checkbox. Clicking this will enable loose particle detection. If you click on the loose particle waveform, a separate waveform will be output to the memory list that's the recorded time waveform minus the stimulus. So listening to this will actually sound just like the loose particles. Selecting a relative envelope has a steady state at 0. This makes the threshold become relative to the steady level state as well. This would allow you to utilize a standard detection threshold independent of the test level. On the other hand, absolute will reflect the response level. Averaging time is the width of the running RMS averaging applied on the time signal to generate the time envelope to detect the loose particles. The maximum and minimum duration will allow you to ignore transients which don't fit within these limits. In this case, we have a 5 millisecond minimum and a 15 millisecond maximum. This first transient is rejected. It's below the minimum duration. The second is between 5 and 15, so it's accepted. And the last one is rejected because it is above the max duration of 15 milliseconds. All peaks that exceed the threshold are counted as loose particles, as long as they also fit within the min and max duration. This threshold must be defined and set high enough to exclude random background noise. Using a good known speaker, you can choose a level above the background noise, and then measuring a loudspeaker with known loose particles can verify that the threshold is actually exceeded. And to avoid the false peak detection, the hysteresis level should be set to a value greater than the background noise. As you can see, there's 6 points that cross over the threshold. But if we give a negative 6 dB hysteresis value, the loose particle algorithm will only give us back 2 failures. It ignores the peak over threshold until the sound level goes 6 dB below. The max stimulus frequency is just a low-pass filter. Because loose particles happen at the lower frequencies, we can use this to cut off all high-frequency information. Let's take a look at how loose particles work in a sequence. When we run this sequence, you can see it outputs a loose particle envelope as well as a threshold. Every time that threshold is exceeded with the characteristics we defined in the algorithm, the loose particle count will increase. Here, the loose particle count is 12. A common method would then be to run this value through a limit, and if it exceeds the limit, the step fails. So this sequence, if we're ever above 2, it fails. This speaker is pretty bad, so it fails. I'll also play back this loose particle waveform that gets output from the algorithm. If you want more information on loose particles, we have a couple AES papers available on the Listen website.